When you have a two-variable data distribution, it's always a good idea to plot it on a Cartesian plane. So what you see here is what we call a scatter plot, which really has zero correlation, which means that the data points are kind of all over everywhere. This Cartesian plane would indicate a strong linear correlation because you can see that our data has started to group together and form a straight line. But instead of qualifying our data in terms of weak or strong, we can actually quantify it by finding what is called the linear correlation coefficient, which we use the letter R to represent, as you see above. In the case of zero correlation, the R value would be equal to 0. So it's the scatter plot we saw earlier where there's no real correlation between the data. Weak linear correlation would correspond to an R value of approximately equal to 0.5. So you can see that the data is starting to group up a bit. If we have moderate linear correlation, then we're looking at an R value of approximately equal to 0.75. So you see that our data is grouping even more, trending in a linear way. A strong linear correlation would be an R value approximately equal to 0.87. And you can see that once again, the data is really grouping and starting to form a straight line until we reach perfect correlation, which would be an R value equal to 1. Perfectly straight line, data all grouped up nicely. But we need to be careful because you can actually get a negative linear correlation coefficient. And in that case, with the linear, what that negative is indicating is that our data is doing the opposite to one another. So when X is increasing, Y would be decreasing, and vice versa. Which means that overall we would be seeing that our data is decreasing. But once again, a zero correlation would be an R value equal to 0. A weak linear correlation is going to be an R value approximately equal to 0.5, but this time it's a negative 0.5. You can see that the data is starting to group as it did previously. Moderate linear correlation is once again 0.75, but this time negative, so negative 0.75. Strong linear correlation would have an R value of approximately equal to negative 0.87. And you can see that line really starting to form there. And finally, we have perfect linear correlation with an R value of equal to negative 1, with strong straight line going downward. It's really important to note that those R values are actually equal in strength. So an R value of negative 0.8 is equal in strength to an R value of positive 0.8. The difference is that the negative R value is going to be decreasing and the positive R value is increasing. So you might wonder, how would we calculate the linear correlation coefficient? And one of the ways, if you really want a precise measure, you could use a computer program that uses algorithms to do the calculations for us, and that would get us a super precise value. Most of the time, though, we can make do with an estimate, and that's often what we do with our math problems. So to get that estimated value, what I want to do is actually draw a rectangle around all of my data, and I want to make it the smallest rectangle possible that can contain all of my data points. So that's what you see here. You'll also notice that I've drawn a regression line through the middle of the data. That's what I build my rectangle around. And then I'm going to measure the length and the width of my rectangle and put that into our equation here. So the linear correlation coefficient is approximately equal to plus or minus, in brackets, 1 minus the small side or the width of the rectangle over the big side or the length of the rectangle. And that positive and negative, remember, is just indirect. It's indicating the direction that the data is trending. So in a positive situation, the data will be increasing, and a negative R value indicates that the data is decreasing.